Hello and welcome everyone. Today I, Rudra, Yash and Abdullah are here to present a presentation on Dragon Diffusion, enabling drag style image manipulation on diffusion model. Next slide please. The flow of the presentation is as follows. Firstly, we will talk about the overview of the paper, then method and structure, and at last experiments and results. Please change the slide. As I told you earlier, this is a new image editing model allowing drag style manipulation on diffusion models. Change this slide, please. This method is more flexible as using this one can edit in various modes like moving, object resizing, etc. Change this slide, please. There are also some of the existing state of the art methods like StyleGAN, which uses generative AI for image editing. This is the architecture of DragonDiffusion. It uses guidance and generation branch. The guidance branch is the usual diffusion model, whereas the generation branch is responsible for the editing of the image. Now I would like to ask my friend Abdullah to continue the presentation. Thank you.
So the model is basically two parallel branches, two parallel stable diffusion models, a guidance branch and a generation branch. Stable diffusion is made of an autoencoder and a unit denoiser. So the image goes through the encoder of the autoencoder to encode it into a latent representation, and then all the editing and diffusion process happens inside of that feature space, and then it goes through the decoder to reconstruct the image. So what we're trying to achieve here, our goal is to edit images while preserving content and texture of the original image. To do that, we take advantage of a feature that has been proven in previous papers and researches, that similar features in different images have similar features in the intermediate feature space. And by intermediate feature space, I mean, we know that the diffusion process is iterative, like it happens in time steps. So an intermediate feature space is the feature space of an intermediate stage inside that diffusion process. So similar objects have similar features inside of that feature space, and they highly correspond to another. So what we're going to do is we design a score function, a loss function, based on that principle to transform the editing signal into gradients, and then transform the content information from the guidance branch to the generation branch through cross-branch attention. It's also worth mentioning that all the editing and diffusion process is dependent only on the feature correspondence of the image itself in the model, so it doesn't require any task-specific fine-tuning or extra training. So we know that strong correspondence can be used for point-to-point matching because similar objects in different images have similar features. So we can use this similarity to measure like similarity of features in different images to match them point to point. So what we do is we use in this model, we use the unit denoiser to map the intermediate representation of the two branches, the guidance branch and the generation branch, with the feature space from these two branches, from the denoiser of these branches. So let me explain that here in an example. So what we're going to do is we're going to create three masks: mask guidance and mask generation. So as you can see in the original image, we have an image of a coffee on a cup of coffee on a table, and we want to edit it. We want to move that cup down below in the image. So the guidance mask is going to be the place of the content that we want to move inside of the original image, and the generation mask is going to be the place that we want to move that object to, the place of the object inside of the edited image. So what we're going to do is we're going to map the features of this particular mask inside the guidance mask inside of the original image and compare its similarity with the generation mask inside of the edited image. And if these two features are similar, that means that the object has moved from the its original place into the editing place. And we do that by measuring the cosine similarity of the two features. And since cosine is between -1 and +1, we add 1 and divide by 2, so to normalize it and make it from 0 to 1. And so The higher the similarity means the better that the object has been edited and moved. And also we made something called mask share. Mask share is simply everything except of these two masks. So it's basically it's the content and texture of the original image that we want to preserve during the edit. So as we can see here, the similarity in the mask guidance feature and the mask generation feature, the higher the similarity, the lower the loss. And the same thing happens in the mask share. The higher the similarity in both of the image inside of the mask share, that means we preserved more content, which is going to make the loss even lower. So to do that, we used guidance from the features of the unit denoiser inside of the stable diffusion in both branches. And as we know, the unit denoiser has 4 blocks of different scales. So the authors wanted to find out which blocks should they use to get the best outcome. So they made an experiment, which is to set the input to a generation branch as random noise, and set the mask generation and mask guidance into zeros. So they told the model that there will be no editing at all, and mask share to be all ones. So basically what they did was they used the generation branch being guided by the guidance branch to reconstruct the image, simply reconstruct the image with no editing at all. And as you can see here, we try to reconstruct the cat image on the left, and what they find is that the first layer inside of that denoiser contains too much semantic information. Like it contains the idea that there's a cat in the image and the cat is on a table or a stair or whatever, but it doesn't preserve any kind of texture or details whatsoever. And the last layer, the fourth layer, it has been through so much convolutions that it doesn't have high correspondence anymore into the features of the original cat. Both the second and third layer have balanced semantic information and content details. So what they did is they decided to use a combination of the both, and that led to the best results, which you can see in the last image on the right. After using both the second and third layer, they tried to edit the image, and as you can see in this example we have here, they noticed that there are still traces of the original object in the place where it was in the edited image. So they decided to create a contrastive loss that makes the model get rid of all traces of the original content inside of the place where it was edited from. So they created something called mask inpaint, and mask inpaint in general is basically the same as the guidance mask, except it doesn't contain the pixels where it's shared. If the mask guidance and mask generation are both have a shared space, it doesn't contain that space. But in this example where they're both far from each other, it's basically just the guidance mask. So what they do is they measure the similarity of the features inside of the red circle in the edit image and the features of the original object in the original image. And if these two features have high correspondence, that means that the original content has not been correctly removed from its place. There are still traces of it there. And when there's high similarity and high correspondence, as you can see in equation 7, the loss will increase. So that way we're teaching the model that also while editing and moving the object, we should remove the original content from its place. And by that, we'll see some more experiments and results. From our
So
friend
coming to the
Yash.
experiment, from coming to the experiments and results slide, the model can move an object from one location to another as shown in the picture. To, to preserve the content, a contrastive loss is added to the editing and the preservation losses. The contrastive loss ensures that the generated result do not preserve the content as it was there in the original position in the image, which means if the loss is smaller, the object has moved away from the position as it was in the image, and if it is higher, it means that the object has tape around it. Next slide, please. Next. Next slide, Abdullah. Yeah, and in this example, you can see in this example, the task of the model aims to replace the appearance of the objects of any category belonging to the same class. The guidance branch involves the diffusion of two guided images, the original image and the appearance image. In the above images, you can see how beautifully the model blends the color of the red fruit with that of the yellow fruit and creating an image with no distortion. Next slide. Over here, we have talked about how the model can help in dragging image content via a specific point in the image. The starting and destination points along the adjacent points are set along different locations, and the gradient guidance for this task is obtained through the default laws that we have talked before, that is the contrastive laws. Next slide. Now talking about the pros and cons of this model. As computation power continues to improve, there is a high potential for optimizing DragonDiffusion to enable real-time image editing. It can also be integrated into interactive image editing tools, allowing users to make real-time adjustments and see the results instantaneously. Even though this model is resource-heavy and produces some inconsistency in object replacements, further research could be directed towards enhancing the efficiency and computational speed of the method. Next slide, please. Now talking about the future prospects of DragonDiffusion. This slide majorly talks about the future prospects in which DragonDiffusion finds its usage, like medical research for identifying tumor boundaries, environmental sciences, and in creating high-end gaming graphics and animations. So this brings to next slide, please. This brings to end of our presentation. Thank you. We are open to any questions that you may encounter. Please ask.
Hi, can you hear me?
Yeah, I can hear you.
Yeah.
Yeah, so I wanted to ask in the contrastive loss section, how does the model the location of the original object if in there's part of original object still there?
I'm sorry, I didn't hear your question correctly. Can you please repeat that? Can you please repeat your question? I didn't hear it right.
Yeah, can you hear me now?
Yes, yes. I can't hear you if you're speaking now, so I don't know exactly.
Hi, yeah, sorry, it's my network. Can you hear me now?
Yes, yes.
Yeah, so here, how does the model, I wanted to ask, how does the model account for the location of the original object that is still there in the result?
Well, we first create two things, which is the guidance mask and the generation mask. Okay, so these things we create when you want to edit, like we mask out the cup like manually, and then mask out where we want the cup to be. So we create both the guidance and generation mask manually. The in-paint mask, which is used here, is everything, you can see it in under equation 7, is everything in guidance mask and not in generation mask. Basically, in this example here, since we want to move the piece of bread from a place to a completely different place, then these two will be separate. So the imprint mask will just be the guidance mask. But if these two are touching, like if we want to flip the piece of bread, so it's vertical and not horizontal, so some space will be shared. So in that case, we want to remove the features from this shared space, would only remove the features from the separate space, the space between them. So what it does, it compares. So if you can see at the equation on the right, the equation on the bottom right, so the features from the generation mask, we're gonna use is the red circle, is the features inside of the red circle, and the features from the guidance is the features of the original object. Okay, so we compare these two features, and if they have high similarity, that means that there are still traces of the original content inside of that place. So the loss will increase. That way, we're telling the model to remove these features to make it as less like correspondent and less similar as possible.
Got it. So according to the relativity of how corresponding the masks are, the model will remove the guidance feature. Is that what you're saying?
The features inside of that mask, inside of the space of that mask. Yes,
Yeah, yeah, got it. Thanks.
thanks. So, any other questions?
Hi, can you hear me?
Yes.
Yeah, I just wanted to ask, is there any technology which can be used to find the recreated image by using this one?
That can be used to find what? I'm sorry. Can you please repeat the last part? Is there a new technology that can be used to do what exactly?
Okay.
I didn't hear your question right. Can you please repeat?
Hey, Kim, may I ask question?
Yeah, go ahead.
Okay, so like my question is very simple. Like if we do implement this code, so how long it would take in a computation time? What would be the computation time, or how much the power of the computational GPU unit would it consume? If we're going to, does it cost us or not? Is that economically feasible?
Well, as we said on the cons here, the model surely will be relatively slow because it uses two diffusion models, and so it's large, and also the diffusion process and the editing process is iterative, so it's gonna have to work on steps. So you can assume it's like using a normal diffusion model, but like almost twice as slow. So it will require heavy computational power, and it will take time.
So is there any kind of possibility if we add the onyx layer on it? So would it be the good, and like during the inference, would it increase the
I'm sorry,
computation
Your voice is breaking a lot.
uh,
your voice is
time?
disconnecting. I can't hear your question.
Is that
Yeah.
possible on this model? Like there is, okay, like there is like ONNX layer, like open neural network. So would we have to at that layer or the end of this model? Is there any kind of possibility to increase that inference?
Well, it will still be a large model. Like, I'm not sure I completely understand the question, but I'm sure if we add like more network, that will make the model even bigger. So that will probably use more computational power and not less. So does anyone have any more questions? Okay, I think we're done for today. Thank you all.